All right. As promised, we can add some complexity, a lot of complexity, to our basic linear model to capture a whole bunch of interesting things and important facets of reality that we otherwise can miss. So today we're going to talk about multiple linear regressions, which is an exciting extension of what we've been talking about, and a way to start building some of these models that are really interesting and complex. All right, so as a bit of motivation, I find medical studies are rife with these things. So we're going to start with a fun, dramatic medical example. Recently, numerous studies showed that women who took hormone replacement therapy had a lower than average incidence of congestive heart disease. All right, so sounds like the kind of thing that you should go, prescribing hormone replacement therapy for women who have no need for hormone replacement therapy, but who perhaps were concerned about having congestive heart disease, right? Sounds good. Except they forgot to do something in this study like control for income. Once they controlled for income, the results showed that hormone replacement therapy actually increased congestive heart disease. I particularly like this example because it was such a dramatic reversal of the findings of this study. There's other interesting ones like this out there. There's one that's a bit graphic. I'll save it for a conversation in class. But right, these kinds of things happen where you look at them from one angle and it looks like there's this relationship. But when you actually take things into account that are important, you find that there's actually the opposite relationship. Why is income so important here? Well, hormone replacement therapy is a treatment that often isn't covered by people's insurance. So who do you think gets hormone replacement therapy? People who can afford it. The other piece of that is who would tend to have more congestive heart disease, or who would have less congestive heart disease, right? People who can afford to take care of themselves have less congestive heart disease. And so that's why you see this dramatic reversal in this example. Perhaps less dramatic, but closer to home, a model of the impact of bonuses on enlistments. This is a really hard thing to study. How much does offering a bonus help us get new enlistees? Well, one model found a high degree of sensitivity to these bonuses. Great! We should offer more. Well, actually, we need to offer just small bonuses and we'll get all the people we want. One thing the initial research was missing was that they needed to account for unemployment rates at the time of enlistments. That it turns out unemployment has a lot to do with whether or not people are willing to enlist. And so if you happen to be offering these high bonuses at the time that there's also high unemployment, you get all these enlistees. And it sounds like bonuses are the driving force here. But there are other conflicting things that are also having an impact. And so we want to try to think about these things and take them into account in the way we study the world with data. Now, here's the trouble. Here's the real kicker. When we omit important variables, we can bias our results in a whole bunch of different directions. We can find some of those spurious correlations or exaggerations like we looked at last week. We can miss important results because we failed to control for missing variables. The ability to control for many variables is one of the powerful things about regression analysis. Arguably, controlling for missing variables may not be powerful enough, and we're going to talk about some additional causal methods to really try to hone in on causality next quarter. But unless you're running a controlled experiment, at the very minimum, running a regression where you control for omitted variables is an important thing to do. All right, let's take a look at an example of what happens when we try to figure out how to right-size a training program. We want to budget for a training program. This is an example near and dear to my heart because this was the kind of one of the first jobs I had in the Department of Defense was to try to figure out how to help out some folks sizing their budget when they had a lot of variability in what they were budgeting for. And some of the variability was built on trying to right-size a kind of training program to get people to pass their exams. So in this training program, people have variable training hours for a couple of reasons. One of the reasons in this training program is because of things like holidays. So people show up for a 5-week, whatever, training program, and it looks like a little longer than 5 weeks here, maybe 8-week training program. And there are some holidays, and the holidays aren't evenly distributed. So if you happen to come to the training program during holiday season, you're going to have a few fewer training hours. The other reason you might have more or fewer training hours is because of extra help. So that while if you're struggling, they give you some extra training hours to help try to get you over that finish line. So for those people who are struggling, the extra training hours might help, but they probably started out with lower test scores in the first place. At any rate, so there's some variability in training hours, and we know that variability is key to being able to run a linear regression. And we want to see if more training hours improve people's test scores. Fair question. We also have some information on their AFQTs, or their IQ tests. So let's look at a simple linear model. Here we have training hours as the variable to predict test scores. What this model is telling us is that for every increase of a training hour, test scores, on average, increase by about 0.16 points, on 7 points. So for about every 5 additional training hours, people get about an extra point on the sort of final exam in the class. This is statistically significant. You look at that p-value, it's 0.002. So it's not quite significant at the 1% level there, right? But it's significant. It is significant at the 1% level. It's not quite significant at the 0.01, at the 0.1% level, but still a fairly significant, highly significant result. So smallish impact, though perhaps you could think of it as what would an extra week of training buy you? And then it would look like you'd get a significant increase, like a meaningful increase in that score. All right, so here's how we might model that. Let's say we want to look at what on average would someone score if they had 150 training hours, and they'd get about a 59.3 on the exam. If we tacked on an extra 40 hours of training to this program, how much more would they score? Well, an extra 10 hours is going to score an extra 1.6 points, so an extra 40 hours, right, just slightly shy of 8 extra points, which might be enough to matter, right? All right, so, but let's take a look here at, we're going to add an additional variable. We're going to add the AFQT score to see if that tells us something about how people are going to do on this exam. So why might it matter? Well, if part of the reason, one, it could help us predict who's going to succeed or fail, but why it might matter as an omitted variable is that AFQT score could be related to struggling in the program. So if the people who are struggling get more training hours, and those same people who are struggling, right, have lower AFQT scores, then we would expect that omitting this kind of variable that measures in some way aptitude. And again, I'm not going to argue that AFQT is a perfect score measure of aptitude. We could get into a big argument about that. Good thing this is a video, so you can't argue with me right now about it. But put the arguments on the shelf for a moment. Let's just say it's a decent way of measuring aptitude, and that people with lower aptitude are struggling more in the program and getting extra training hours. We could be exaggerating the impact of training hours on or in this case, underemphasizing the impact of training hours on how well people do on the test. So basically what it's saying is that if low aptitude people get extra hours, they're struggling more on the test anyway. So if you gave everybody, extra hours, people would do even better. And that's what the findings here show. If we take a look from Model 1 to Model 2, that coefficient improves a little bit. It actually is more statistically significant and also a slightly bigger impact from an extra training hour on test scores. AFQT is significant, and so it matters, right? Some sort of measure of aptitude is a reasonable measure of how well people are performing in this program, is what it's telling us. Also statistically significant, both of those at the 1% level. Some other things you might notice is that that adjusted R-squared down there at the bottom, we talked about those a little bit last week, has improved dramatically. So you went from explaining about 4% of the variation in test scores to about 27, 28% of the variation in test scores, looking at those adjusted R-squareds. Right, we can use the new model to predict test scores just like we did with the old model. Here we have 150 hours and we want a percentile score on the AFQT of 80. We plug those into our model just like we did before, and we get a predicted test score of 65. So we can ask questions like, what happens if we were to increase training hours by 10, or how would having an AFQT score 10 points higher affect the score? And so, right, an additional 10 training hours would get you 2.2 points, and increasing AFQT scores would get, by 10, would get you an additional 4 points on these tests. All right, so we can add additional continuous variables, we can add lots of them, and we can make predictions at certain values, right, for all of them. We can estimate prediction intervals and confidence intervals just like we did before, and hopefully get models that are more precise, right, do a better job of explaining variation, and also that control for these important omitted variables. In addition, something we can do with these models, we talked about before that one of the things in linear models is that if you have nonlinearities, how do you deal with them? Well, the first and simplest nonlinearity we might want to deal with has to do with adding what we could call categorical variables. So here I have a picture of a cost estimating relationship, which is a regression used to predict the cost, in this case, of the engine of an amphibious assault vehicle. And here we're using horsepower to predict costs. Here's the data. So the data tells us something about horsepower, something about cost, and something about the type of the engine. And we might want to include this information about type in our model. If you take a look at our model, it looks like there's kind of two chunks in that model that need explaining, and then that line is kind of connecting two pockets of data. So let's see what we can do with it. We might want to estimate a model that includes this second variable, type, but we can't really put those words into our model. So what we need to do is create a categorical, or what's often called a dummy variable, to handle it. You need to code this 0 and 1. So it doesn't matter which one I choose, as long as I pay attention to which one I choose. So in this case, we've taken those diesels and we've made them zeros, and gas turbines and made them ones. You can do it the other way around. You'll just approach it a little differently in the final math, but it won't really matter. Must be 0 and 1s. 1s and 2s will give you different answers, and a little bit wacky. So choose your 0s and 1s, and essentially what you're doing is you're modeling now two parallel lines. So the same regression for both, but with parallel lines or different intercepts. If you want a picture of, I think this is kind of a neat picture of what omitted variable bias does, because in the first one you have this really steep line because of the omitted variable. In the second one, those lines are much flatter once you control for the omitted variable, in this case the type of engine. We can run both models. Here they are side by side. You see that that slope coefficient on horsepower is much flatter, going from 94 down to 44. And that type seems to matter, so what it's telling us is that essentially those gas turbine engines are about $63,000 more expensive than our diesel engines. Both of those are statistically significant, right? So those p-values that are teeny tiny there at the 1% level, and our R-squared cost estimating relationships have these ridiculous R-squareds. Never in my analyst life have I been lucky enough to have such majestic R-squareds as you do, well, with time series and cost estimating relationships. Here we have a 0.8. Before, in our adjusted R-squared, it goes up to 0.991. So we're going from explaining about 80% of the variation in the cost of this engine to about 99% of the variation in the cost of this engine. You see the standard errors shrinking kind of along the same lines, which is going to shrink our confidence intervals. And so we can use this information to predict either kind of cost. Essentially what you're going to do is, if you have a gas turbine engine, you're going to use the equation like you've used it before, beta naught plus beta 1 times the horsepower that you want to estimate plus beta 2 times 1. If you have a diesel engine, you're essentially going to drop out that added cost that comes from having a gas turbine engine, and so you're going to use beta 2 times 0. Now, we aren't constrained to one category. We can add multiple categories. So here we have another cost estimating relationship. We have helicopters, and we have 3 types of helicopters. I believe transport, attack, and search and rescue helicopters in that type category, TAS. Again, can't really run a regression on them. Well, we can, because R is smart, and it will take our categorical variables and essentially turn them into dummy variables for us, but just for the moment, we can't. All right. We can include all of these as dummy variables. Essentially what we do is we keep a base case of 0, and so we'll have essentially 2 dummy variables for 3 categories. Doesn't matter which ones are which, but you're going to make up 2 new ones, keeping in mind. So here we used transport as our base case. We have attack helicopters and search and rescue helicopters, each sort of with a 1. So in the attack helicopter column, if it's a transport helicopter or a search and rescue helicopter, it's a 0, and an attack helicopter, it's a 1. In the search and rescue column, similarly, if it's a transport or an attack helicopter, it's a 0, and if it's a search and rescue helicopter, it's a 1. We're going to put both of those in there. So essentially, if we want to estimate something about a transport helicopter, we're going to set both of those to 0. If we want to estimate something about a search and rescue or an attack helicopter, right, we're going to set the relevant categories to 1. So here you go. Here's a picture of our output and our equation, and we can use that again to estimate whatever we want to estimate. Right. We can also include nonlinear variables in our models. So to include nonlinear variables, the one on the left kind of goes up for a while and then it goes down. We're going to include that with a quadratic term. The one on the right, I'm an economist, so I love the law of diminishing returns. The law of diminishing returns implies you have these kind of things that go up and then they kind of flatten off. And that's what we're looking at on the right, otherwise known as a logarithmic model. So logarithmic models are fairly common to encounter. When do you want to take a natural log? Here's some ideas. One, you might want to take it when the variable is very large. We often do use logarithmic models to shrink down really big data. So things like population, gross domestic product, defense expenditures, these are often used in natural log form. We might want to do it when we want to know things in percentage terms. So logarithmic models give us a percentage increase in one variable into a percentage increase in another, or a unit increase in one variable into a percentage increase in another. So things are in percentage term. If you log it, it's in percentage terms. Log models also are kind of cool because it doesn't matter what scale of the variables you're using. Scale can be something you really need to pay careful attention to. Log models don't care because they're in percentage change terms. If you see data that looks like a logarithm, that's another good reason to use a logarithm. Oh, part of that data that's very large, I should have said, is also outliers. If you have a lot of big outliers, logarithms tone them down. And there's another kind of more technical reason. They're useful for controlling for something we call heteroscedasticity that we're going to talk about a little later. And so we're going to use them when our data is skewed or heteroscedastic. There's some variables you can't take logs of. So a couple of them, you can't take logs of years. It doesn't really make sense. Log, like the percentage change in years, doesn't really even make sense to talk about. So it wouldn't make sense to do it. variables that are proportions we can't take logs of because they're already sort of fractional, and like what's a percentage increase in something that's basically a percentage? Like that's kind of weird, right? Like a percentage change of a percentage. And that gets us to our final one, variables that are in percentage terms. We can't take logarithms of those either. All right. Just to give you a kind of picture, it's very easy to implement these in R. Here's a formula that's predicting scores on math tests in 10th grade as a function of the compensation and staffing of schools. Right, the first model uses all of the straight numbers. The second one, we simply use the word log, and R smartly turns them into logarithmic output. You'll notice that the numbers are very different, and we have a very different way of interpreting them because we're getting at percentage changes. So while this first one tells you that a $1 increase in total compensation increases math scores on average by 0.004586 points, this one tells you that a 1% increase in total compensation increases math test scores by about 21 points. So it's giving you very different information. I actually really like, so just like in this model, we can take the logarithms of the variables on the right, we can take the logarithms of the variables on the left, and there's some different ways to interpret them. And I really like this chart and I always turn to it when I have a logarithmic model because it helps me keep track of what I need to do in order to do what I say I'm going to do. So level models are the ones you've seen before. A change in y is equal to beta 1 times a change in x. If you have a level log model, you're looking at, on the one hand, a beta 1 change divided by 100% change in x is equal to the change in y. So I actually made a mistake in how I spoke of this one. So a 0.2, a 0.2 or a 1% change in total compensation leads to a 0.2 point increase in test scores, because we divide that 21 by 100. We can have a log on the left compared to a change in x on the y, and so then you would multiply that beta 1 by 100 to get times the units. Let's say 1 unit change in x, would lead to a beta 1 times 100% change in y. And then you can have log-log models where you simply can interpret them as a percentage change. So a 1% change in x leads to a beta 1 percentage change in y. Find that handy. It's a little confusing and overwhelming at first. We'll practice it. I think that's the only way to make it kind of work. And then if we weren't making things confusing enough, we can add into our lives an x squared term as well. So here we have a model where we've put things in terms of x's and x squared. When this happens, we can't interpret the model because the relationship of x and y is changing over the course of the model. It's not so simple to interpret. So we need to know where we are in terms of x in order to figure out how much y is changing with x. So at first, if it's going up, it's going to have a different slope, and it's flattening out, a slightly different slope. And then if it's on the downhill side, so you need to know where you are in the model in order to know what the effect on y is of another change in x. So essentially what we need is some calculus to do it, but let me give you some answers, So instead of worrying so much about doing the calculus, this gives you kind of what the derivative would be, and therefore what the answer is in terms of the change in y according to a change in x. Well, it depends on where you are. So instead of just beta 1, it's beta 1 plus 2 beta 2 hat x. So you'll need to know where you are, and that'll give you how much y is changing at any given point based on another change in x. So sometimes these models, right, go up and then down, right? This one, y is increasing in x at first, and eventually will turn around and be decreasing in x. This is like an upside down U shape. And so, we also might want to know, where does that turning point happen? And that's what this formula x star gives you, is that turning point is at beta 1 hat divided by 2 beta 2 hat. And that's, right, setting that first derivative equal to 0 if you want to go back to calculus class. If you want to forget about calculus class, here's a formula for you. You can have one that's decreasing and then increasing, and here's a formula for you as well. All right, so these were a lot of different things you can do. We're going to practice them and incorporate some of these other things in our models and practice interpreting the coefficients and making predictions from them. The computer will solve a lot of those problems for you in making your predictions, but making appropriate choices in terms of what variables to include and how to make sense to them is important. Still, there's a lot of choices to make. There are even more than we've talked about, and we're going to talk about some more choices and how we can make those choices next time. The other thing that we might want to think about is what to do if things like the response variable aren't linear. We're going to talk about different kinds of models to address things like that and other kinds of problems that we encounter. We're going to address technical challenges in these kinds of models. But I think that how you make choices is important. And so we're going to take a first stab at that coming up shortly. And we'll revisit that issue next quarter when we talk about sort of more complex model selection processes. A few caveats. The kinds of things that we talked about today have sort of logical reasons for being, and there are logical reasons to include them. Some of the choices we can make for our models have to do with the data and not the underlying logic. There's nothing necessarily wrong with that, but that's a choice that we make in terms of how we do data analytics, and is a choice that we're going to talk about making explicitly when we look at those kinds of models next quarter. All right, so with that, we'll come back and talk a little bit more about how we make those choices next.